Okay, so just as a review for Monday, because we had that day break. Okay. Exponential functions, how do you know it's exponential? The variable is in the exponent. So we studied in first semester things where we had exponents, but they weren't variables. They were numbers like x cubed, x to the fifth, x squared. Those are polynomials, not exponential functions. In order for it to be an exponential function, the variable has to be in the exponent. And then we talked about, really there's just one formula, right? Y equals a times b to the x. But you have to pay attention to the value of b to decide if it's going to be exponential growth or exponential decay. Now, did we also talk about at the end, like with the graphs, that growth does not really mean increasing, like going up? And decay does not mean decreasing, going down? It just so happens that, like, if we only look at the simple graphs like we did on your homework, all the growth functions are increasing and all the decay functions are decreasing. But when we talk about growth and decay, we're not referring to the graph as increasing or decreasing, we're referring to its rate of change. So on the sideboard over here, I hope I mentioned on Monday that when we say exponential growth, if we were to look at slopes between points, like they're getting bigger, right? The rate of change is getting really different. And then if we were to do an exponential decay, the slope is getting smaller each time. So it drops, and then it drops, and then it drops. And then it's like you hardly notice it's dropping at all because it looks like a horizontal line. Okay, so just as a side note, if the base is positive, if the A is positive, all the growths will increase and all the decays will decrease, but we can have reflected graphs. So that will always be the case. Here's what you need to know for today. So I would put this into your notebook for today. The real world model is going to sort of amend our old model. So we're going to say today we're basically using the same thing, y equals a times 1 plus, or y equals a times b to the x, but we're going to replace b with 1 plus or minus r. And I guess I replaced the x with t. It could be x still. A lot of times the exponential models are going to be related to time, so t represents time. Okay, so I'm going to label a few things in my real world model. R is going to be my rate of increase or decrease. If things are increasing, I'm going to want to use the plus sign. So like if I'm earning interest or paying interest, I'm going to do a plus. And then if things are getting smaller, like you buy a new phone and then a new version of the phone comes out, or you're using your phone, your value of your phone decreases, then you're going to do minus. So R is the rate of increase or decrease. Now, make sure when you plug this into the model, if they say like it increases at 10%, make sure you change that into a decimal. And we also saw that in relation in the geometric sequences, like for the salaries. Remember, like if my salary is going to increase by 5% each year, I am still getting my original salary plus 5% more. So I'm getting 105% of my salary the next year. And then the same if that continues. Okay. T is time. usually in years, although just read the problem and decide. There are some problems like medicine. So like when you take a dose of medicine, then you have a lot of medicine in your bloodstream, and then as the hours go by, the amount of medicine in your bloodstream reduces. So we wouldn't use years for how much medicine is left in your body, we would use hours. So it just kind of depends from problem to problem. Okay, and then A in the real world model, the best thing I could say is to always think about A as, if you imagine for time, what if I put in 0? 0 in time would be at the very beginning of something. If I put in 0 for my exponent, what happens to 1 plus or minus r raised to 0? It's equal to 1, which is equal to A. So we often call A in this model the initial amount. Or you might also write it's the amount at time 0. Like the starting amount. Well, no, that would be equal to 1. And your starting amount might not be 1. It's A times this thing to the 0. 1 plus or minus r to the 0 is 1. But 1 times A is A. Here's our first example. Now we're going to have dueling knuckles. No? Nobody else heard all the knuckles?
Oh, people cracking.
Now we'll have the dueling knuckles.
It's like everyone has like the impulse to do it once you say it.
Good job.
I know, I'm sorry. My apologies. Okay. I would jot some information down. If you want to like abbreviate it in your notes, you can. Okay, but jot some things down here. Okay, it tells us in 1980, about 2,180,000 workers worked at home. During the next 10 years, the number of workers increased, well, the workers working from home, I suppose, increased by 5% each year. Write a model giving the number of workers, W, in millions, working at home T years after 1980. So that would mean T equals 0 is the year 1980. Okay. So T equals 0 is the year 1980. And then something that I want you to be paying attention on in like different word problems is, I chose this example and I worded it this way on purpose. When it says write a model for the number of workers in millions. So when you see that and it says like, this variable represents the number of people in millions, it means you get an answer back out that's probably like 1.3. There wasn't 1.3 people, it was 1.3 million people. Okay? So I actually gave you the full number up here, 2,180,000. What will we use for our initial amount in time 0? Aiden? 2.18. That is 2,180,000. Okay? So we're going to say then that A is 2.18. Now, it wouldn't be wrong to let A equal 2,180,000. It's just the way I worded this example to say in millions, because I want you to be watching for that in some of your answers so you label them correctly. Okay, that's something that I often miss myself. Okay, what else are we going to pull out from that problem?
5%.
The 5%. Which, how do you write 5%? Is it decimal? 0.05. Be careful not to say 50%. That would be a lot of workers.
And an increase.
And it's increasing. So we're going to use plus. Okay, so the number of workers W is equal to 2.18. You could write 1 plus 0.05, but that is also just 1.05. So I'm going to go ahead and do the adding in my head, right, if you're okay with that. Well, this is a great thing. For the model, we want to leave that exponent as a variable, as a t. Because I want to say, like, Nathan, how many workers worked from home in 1992? And Anna, how many people worked from home in 1987? And Luke, if this continues, how many people are going to be working from home in 2010? And so you could put in any year that you want after 1980 and estimate how many workers were working from home. So I like that someone was asking, should we put in 1980? No. Okay. Just remember that T is the years after 1980. Okay. So we might say where T is the number of years after 1980. That would be us being really specific. I'd accept your model if you don't say that. Okay. But I also sometimes, let's talk about this. I also sometimes have people who want to put in the number 10 right there. Why do people want to put in 10 if you read carefully? Okay, so like people are searching for all the things they're going to plug in, and you might read this during the next 10 years. What that means is like we've maybe looked at data. We had the number of people working from home in 1980, and then we kept track the years following. So like we looked at years 1981, 82, all the way through 1989. And we found that the percent of increase was probably close to 5%. It'll probably change from year to year. Or maybe we took an average of that rate of increase. But we're saying we looked through these 10 years and this was the thing that happened. So assuming that rate continues. Okay. So when it says that, it doesn't mean that it only works for 10 years. It doesn't mean that you should plug 10 in for T. It's just like those were the years that we gathered our data from. Does that make sense? Yes.
Now, if that wasn't there, would you put 10 in for T?
If what wasn't there?
When it says write a model, the number of
No.
You wouldn't?
No. The only time I would put 10 in for T is if it said estimate the number of workers working from home in the year 1990. Because then I actually want to know 10 years later. But yeah, that's weird. It's like this weird thing where you see the number 10, you see that it's years, so you want to plug it in. But it's really like saying like, here's where we got our data, and then we're going to say like, we think this trend continues. Now, maybe in 2010 or 2000 with like the internet becoming widely available, maybe we would create a whole new model because if we looked at those years, maybe working from home became way easier, right? So like that model may not, like if I asked Luke how many people are working from home in 2019, maybe this model with a rate from 1980 isn't a very good model anymore and the number is lower than it should be. But we're just writing the model for like assuming that rate continues. That's a good question. It's going to be tough for people. Okay, let's see, next one. see if you and your pods can write a model and find the value of my car after 3 years. I'll give you some time. See what you can come up with. Write the model. Write the model.
Write a model or exponential decay? Same thing.
So A would be 23,000. So it'd be 0.75 for the like 1 minus R, right?
Well, okay, so this one doesn't say that same like phrase like in
I knew
millions.
that.
Right. So you can write it as 23,000. I saw one group had 23, so they're writing it in thousands. But I probably wouldn't write 23,000 in millions. You know. So like you could use, you don't have to change it. I just did that on the last one, so you would be okay with it.
Oh,
That seems
wrong.
Oh wait. No. Just your temple.
Oh wait,
There's a
I'm not-
decimal.
Yeah, I read it wrong. I read the, yeah, okay. Did you guys get like 14,000 something? Do we have, like, do you want us to leave it like with like the decimal or do we farm it?
I usually just go to nearest cent for money.
Do you round
Okay, I'm gonna share the two models I saw walking around the room. I saw V equals 23,000, and then I would probably do this in my calculator or in my head here. 1 minus 0.15. I just think about it like $1 minus 15 cents is 85 cents, so that's going to be 0.85 raised to t. I also saw, okay, modeling after what we did on the past example, value equals 23 to the 0.85 t. And I would accept either one of those. Just note that, you know, like in this one, the problem would read the value of the car in thousands. Okay, so then you would know that whatever you get as an answer is in thousands. You know, your car didn't cost $23. It would be nice, but would it, or would your car not move anyway, right? Yeah.
Why is that cheap?
Why is it?
Okay, so that would be the other. Okay, so in the previous one we did in millions, and there was just really 2 million. And the rest, the 180,000 was like 1,000. So that would come after the million, so it'd be 2.183. But this, we instead of saying like 2,000 or 2,300, which would be 2.3 times 1,000. This is 23,000. So 23.0. If you had like 500,000, then in thousands it would be 500. That's how many thousands you had. Does that make sense? So, yeah, I probably would write this one just because it didn't say in thousands, so I would probably write that. And then use the model to estimate the value of the car after 3 years.
14.
What'd you get, 14?
Like 124.8.
124.88. Did you follow the rounding rules for 8?
Yeah.
Okay. Okay. Any questions on that one? It's pretty, I mean, like, don't think too much about it, right? Once you write the rule, then you're just plugging it in. Okay. Okay, real quickly with your pots, come up with a story for these two.
Oh my god. So, I bought a car. This is the one from
Try to make one an example that would make sense.
It's a precious metal, right?
Oh my god. And then
I don't even know what metals are considered precious anymore.
Would you
yeah, it was just fun.
Oh, pay decrease.
The bottom of there disconnected. Like I disconnected connected to my I have an Apple computer.
No one knows what 7 times is.
No, I haven't.
How much do you think people would pay for a walk like this without it like
Okay, I'm going to interrupt. I heard some good creative things out there. You know, like if you're trying to make a story that makes sense, you probably have to pay attention to your initial amount and then what's happening with your value, right? Like if it's going up or down. So I heard people talking about house loans or buying houses or cars, the Lamborghini, okay? Something really expensive or really big, right? And then it's going to like increase. People were talking about like mortgage, so like your interest payment maybe is 5%. And then on this one, you know, maybe a lot of people are thinking about a price or some number. This could even be like a town, right? This could be the population of my town, and you know, for whatever reason, people are leaving the town at a rate of 25% each year, and my population is going down. The opposite of Papillion, yes. But where are they all coming from? That's what we need to find out. Theirs is going down.
Do they have to make sense?
One of my friends said
Well, in terms of like thinking about understanding a model, it would be best if they made sense. It was really just a fun activity. Okay, now write this down in your notebook.
compound interest? Bro, I knew where compounds next power it is.
I thought she was pulling up the book and
Okay, the last thing we're going to talk about today is a special formula for compound interest. Well, to answer the question of what compound interest is, let's just first talk about simple interest. So, like the examples on the previous slide, I know like one group was talking about a house loan, $590,000, you got a mortgage, right? And then you're going to have to pay some kind of interest to borrow that money so that the bank is actually making money off of you. And that would be like your 5% there. Okay. So that would have been an example of simple interest. You just calculate, like based on the amount that I've borrowed, calculate my interest one time a year, and that's what I pay you. That's simple interest. Okay, so if you want to make a note, simple interest is really the model that we just looked at. It would be like the amount is equal to P, which I'm going to talk about here in just a minute, times 1 plus R to the T. That's simple interest. Let me say, A represents the amount in your account. Or like you might think about that as your balance, how much you have or how much you owe. So this is a financial formula. P is called a principal And it's not spelled like Mr. Johnson principal, it's PLE. And that's the amount you invest or borrow. So it's like P is the same thing as A was in little a. It's your starting amount, right? Whether it's the starting amount that you borrow or the starting amount that you put into an account. And so simple interest, you take your principal and then you just multiply it by 1 plus, I get plus R, usually you're going to earn interest or pay interest, times T, however many years you have it. Okay, that's simple. Now, notice in this one, okay, we've got R, which is our rate. Okay, so I'll say interest rate. And like I said, it's going to be plus because you're like earning interest or paying interest. Okay, so it's just going to be added on. But there's this extra letter in the mix. That's N. N is the number of times interest is compounded per year. And when I say compounded, I mean like, you know, if you got a savings account, you might be earning interest on the money in your savings account. So when my money sits there, they might give me some of my interest every quarter or every month in the year. So I actually get a little bit of interest put into my account before the end. I don't have to wait a full year to get interest. Okay. And the more you compound, because then if they put a little bit of my interest in my account, if it's in my savings account, then I have more money in my savings account and I'm earning interest on interest. So I'm making more money. Now, in most of our savings accounts, it's going to be very small. So we're not making tons of money. Yeah, you have to be like a billionaire for the like compound interest to be like, whoa,
That's real.
I've made a lot, right? Okay.
Those rich people don't need it.
Yeah, rich people get
Well,
everything.
I guess. Now, for the number of times compounded, you're going to hear some of the same phrases. You're going to hear compound quarterly. Quarterly is how many times? 4. You're going to hear compound monthly. That's how many times? 12 per year. If I said daily, 365 is what we would use. So you could make any schedule and say, I'm going to give you some interest every 2 months, and then N would be 6. Okay. And then, of course, T is time in years. Okay. So really this formula, once you figure out what compounding represents, it's really just a matter of plug and chug. And this is why you need your calculator today. Let's do an example before we leave. I just have the compound interest formula up there so that you guys can see it on this example. Maybe jot down some stuff like you deposit $2,000. You could say annual interest 5%. And we're going to leave it in for 12 years. Now, I should make a little side note here. When we do this mathematical calculation in this formula, we're assuming that we like put the money in the account, leave it there, and don't add to it ourselves. Or we don't take from it, which probably over the course of 12 years, not always the case. Although there are some things financially, like at a bank, you can agree to put your money in what's called a CD. It's a certificate of deposit. And the bank wants it because they want to use your money. And so they're willing to pay you a little bit more if you agree to not touch it. So like you could put $2,000 into a CD for 4 years You can't touch that money for 4 years without paying a penalty on your interest, but they're going to give you a little bit better interest than you would get on your savings account. So like if you don't need that $2,000 for 4 years, you're going to make a little bit more money. So a lot of times like parents might do that, like for a younger person, and then like leave that money sit there, and then when the CD comes due, you can either keep it in the CD or then you could take it all out. Again, you're not going to make millions, otherwise we'd all be rich. But you can make a little bit more.
I'd rather make millions.
Okay, so let's do annually. If you compounded annually, how many times a year would you compound? Once. So this is actually simple interest. I don't need n. N is equal to 1 if I'm doing it annually. So r divided by 1 is just r. And 1 times t is just t. So that's just simple interest. So if I were doing this, I would do the amount in my account is 2,000 times 1.05 raised to the 12. I'll move this up so you can see a little bit. I got 3,591.71. Do you agree? Okay. Now, let's see what happens if we compound monthly. If we compound monthly, what's n? 12. So using the formula, the amount in my account is equal to 2,000 times. Now in this one, I won't be able to just say 1.05 because 0.05 actually has to be divided by 12. They're not going to give me my full interest every month. They're going to give me a 1/12 of my interest every month. And then that adds up to 5%. Okay. So we're just going to write it as this. 1 plus 0.05 divided by 12. And I don't even ever figure that. I just type that into my calculator and instead of parentheses. 1 plus 0.05 divided by 12. That's all I need to type in my calculator. I don't need to round it. Okay. And then we're going to raise it to the what? 144. Why did you say that? N times T. 12 years times 12 compounds per year. So we actually get interest put into our account 12 times a year for 12 years. We're getting a little bit of interest 144 times. Okay. All right, try typing that one into your calculator from left to right. If you use your parentheses, you can just do 1 plus 0.05 divided by 12, and then, like Aiden said, raise it to 144. Make sure your calculator works. This is on you. I got $3,639.70. Let me know if you're not getting that, and I will take a peek at your calculator, see what's going on. So when do you make more money? When you compound, because remember, after the first month, I get a little bit of interest in my account. It's not 5%, it's a 1/12 of 5%, but that money sits there and then earns interest. And then the second month, I get a little bit more interest because I had more money in my account, and then that gets added in and sits there, and now I'm earning interest on more interest. And that just continues every month. In this simple interest version, I have to wait a whole year. My $2,000 just sits there for 12 months as $2,000. And at the end of the year, I just get 5% of that. Does that make sense? So, your homework assignment is on your gold sheet. Make sure that you practice those compound interest problems to make sure that you can do the calculations. Okay.
Do you have a Band-Aid?